to the session on Naive Bayes Classifier. So let's start a discussion with what is a Naive Bayes Classifier. So as the name suggests, it is number one a classifier, or to be more exact, it is actually a discriminant function. We'll talk about this in a moment. Okay. And even within discriminant function, there are different types. So what this Naive Bayes is actually a probabilistic generative function. Probabilistic generative model. Okay. And the third important point over here is that it's a Bayesian model. So it has these three properties. So now let's understand each of these three. So let's talk about discriminant function. So this is a very simple way of approaching things. So if we have a data set, which is suppose x vector, that can have like your x1, x2 and so on and so forth. And this is a y vector. Okay. They are discrete, so y is a discrete variable, so it will have like can have categories, so red, blue, green, or it can have yes or no, 0, 1. Okay, so and x is similar to what we have studied in maybe linear or logistic regression. It may be some thing of omega transpose x. Okay, and then you can apply other functions on top of it. So sum of x of it, and if that sum fx, you can actually do a partition on y. This is a discriminant function, which is for very common definition even for any type of classification task that will do, but a more correct terminology is a discriminant function. Now let's understand the second point. What is a probabilistic generative model? Okay, now pay some attention over here. So we have two types of models. One are generative models. Okay. The second one is deterministic model or discriminative models. They actually both differ in their assumption, and they actually offer different types of view. Even in real-time applications, how do you want to apply it? So if you have heard about the word generative, the generative terminology means that they assume a distribution of the data. Okay, so here is your data. They will use this existing training data of yours, whatever is coming to them, and on the basis of them, they will make assumptions about the distribution of the data. Okay, and then when they are this assumption actually gets converted into your data model, or the model that will be used for predictions. And when the final time of prediction or classification comes, they will just use this model or the assumptions that they have made that best fits the data to actually drive all their predictions, okay, or their classifications, whatever you want to call it. Whereas in discriminative model, if we had done on our session on linear models, and I'll put a link in the descriptions, we had done linear basis functions also, which are more advanced form of linear models, which you can actually have any sort of a function, or if you know logistic regression, they actually directly use the data to do two things. Either they would actually do a likelihood estimates. Okay, so they will have your data, and you will have a maximum likelihood of the data. Okay, or the second way you can do is you can make a loss function, and you can actually optimize or minimize this loss, or you can maximize this likelihood, which means they work directly on your training data. They do not have any assumption of how which data distribution that data comes from. Now both have advantages and disadvantages. So let's talk about this, since we are have called that this is a generative model Naive Bayes. So the advantage of this is, if you have got a distribution, this is an unlimited distribution, which means that suppose if I assume that it's a Gaussian distribution, and from this data I have just got my mu and sigma of the distribution. Okay, and I'm assuming it's a mean central or standard normal Gaussian distribution, which means there is no skewness, no kurtosis. Okay, these features are not available. Okay, then I can come up with something like this. So these are your z-scores, which is x minus mu by sigma. Okay, and then you can draw a plot, and once you've drawn the plot, suppose I had only 20 training data, or say there is a theorem which actually tells you how much minimum data you have for a given data variance on which you can actually fit a particular model. Okay, we'll not go into those details, but assume you have enough points to actually make this distribution. Suppose you have 40 points to fit this normal distribution. You fitted this. Once you fitted it, you can actually draw as many points from this distribution as possible, right? So sort of unlimited data points you can draw from it, and you can actually have distributions on top of that can derive of it, and we'll talk about those conditional distributions as well. Now let's understand the third part, which is the Bayesian model. So we talked about two parts. It is a discriminant function. What does that mean? We talked about it's a generative model. Okay, what does that mean? A generative discriminant function. What does that mean? The third point is a Bayesian model. Okay, so let's do a recap of Bayesian matrix. So it's very simple. If I have my PA, this is good. If I have PB, this is good. Suppose this is what we are talking about. I have prepared a data set for this. I will go deep inside it, but this data set is about systolic pressures and diastolic pressures and a heart risk on that. Okay, so suppose this is our x, which means this is x1 and this is x2, and this is a y vector, which is the risk of the heart. Okay, now if we take the same analogy over here, suppose my PA is my heart attack. Okay, PA is equals to probability of my heart attack, or probability of high heart attack, like let's call it high because that is a discrete variable. PB here is suppose my systolic pressures, systolic pressure being high. Okay, let's call it that way. Okay, so any event occurring in Bayesian analytics alone is called a prior. Okay, and if I call what is PA given B, and B in this particular case is an evidence, so given that we have the evidence that B occurred, what is the probability of now PA given that B is it's given that it has occurred or evidence is available? This is called posterior probability. Okay, if we are talking about A alone without any evidence, that is prior. Okay, and if we are talking about A in the presence of B, that is called a posterior, whereas B is the probability of the evidence or the evidence itself. If we do a reverse of this, this is known as likelihood. Okay, and by Bayes' theorem we have P A by B, A given B, not by B, is equals to P B given A to probability of A divided by probability of B. Okay, this is your Bayes theorem. Now come to set theory, and we'll require the set theory later, but let's discuss a bit about it. Suppose if I have set A, okay, I have set B. Now there could be two conditions. One is that there is an overlap between set A and B, and the second is that there is no overlap between set A and B. Okay, suppose I have 3 data points in set A. Okay, two data points in set B, and in this particular case there is one data point intersecting between them. It belongs to both A and B, set A and B. Here also it is the same thing, but there is no intersection. Okay, so if you remember set notations, if we had a set in like this and we are doing a set of A union B, okay, we would say set of A plus set of B, but that would have counted this item twice, once in set A, once in set B. So we would say minus times A intersection B. Okay. In this particular case, since A intersection B is 0, so we can directly say it is equals to P A plus B, and this is our independent notation. So A is independent of B. Similarly, in the case of probability, it's the same concept, the only thing it will be multiplicative in nature, because probability we have already taken the denominator. So if we are talking about probability of A and B, combined probability of A happening and B happening, in case A has nothing to do with B, these two are independent events, then we can simply say this is equals to probability of A, okay, and then B happening, so multiplied by probability of B. Okay, and if there are n number of events, it will be, you can keep multiplying. This is important to understand from the perspective of this data that we just show. Okay, so what is the probability of this complete data x vector, the first x vector, assuming that the first feature is independent of the second feature? It will be just first feature assuming low and second feature assuming low, and multiply those two probabilities. Okay, we'll talk about that in more details. So one concept is this of Bayesian that we got from Bayesian. Okay, the second concept we got from set theories or probability theories, whatever you want to call it, is this, and we'll be using this extensively. So now let's complete it. So we had in this data the probability of LM, medium and high. So this is the data in which you have systolic pressures and diastolic pressures. Sorry, this should be pressure, not sys. Pressure diastolic and pressure systolic. Okay, so this is low and high. This is low, medium, high. This has 3 levels. This has only 2 levels, and this is my heart rate, which has 2 levels. So if I want to actually make a classifier in this particular case, so I'll have both my probabilities. What is the probability for any data that I have a low heart risk, which is like RL, probability of R being low, and then I will also have a similar probability of R being high. I'll compare these two. Okay, if I am making a single point model which just have one prediction in this particular case, and the data that we have taken has only one predictions, then whichever is higher we'll compare and we'll give that result. Okay, that is our class. The heart risk is that, let's call it high and low to avoid confusion. Okay, so that is my heart risk. But if I have multiple classes, I can also give the probabilities of each of that classes. Okay, so this is also an advantage of naive Bayes, and we'll discuss this in more detail later. Okay, so if I am computing my PR low given a particular data set, okay, suppose I've got a data vector, x vector. Okay, and what is my x vector? X vector is my x1 and x2. Okay, then I can say that this is equal to my probability of x given PR low, R low, sorry, okay, into probability of PR low itself. Let's write it here. Okay, divided by probability of x. Okay, let's call it xi, given an xi, a particular data set. It's not a complete x vector, but a given x. So this is again your posterior probability, this is your evidence, okay, this is your prior probability of PR low, and this one is your likelihood. Okay, so now the big question, why it is called naive Bayes classifier? Why? What is the meaning of word naive? So it is called naive because it has naive assumptions. What is naive assumptions? Very simplistic assumptions that in a data set all the features are independent of each other, or mutually independent. Okay, so for example, we are calling, in the case of the data set that we have taken, that our pressure of systolic and pressure diastolic are independent. And if you talk to a doctor, maybe in some cases they are independent, but in many of the cases they might be related. So this might not be a real world scenario. In fact, if you take most of the scenarios in real world, you will find that it is a very complicated relationship. It is not as simple that you can consider it completely independent. Okay, so because of this conditional independence of the features, this is a naive assumption, so it is called a naive Bayes classifier. Okay, what is the second assumption that it has, which is again a naive assumption, is that all the features contribute equally, which means now we will not distinguish between how much weightage we should give to feature 1 versus feature 2, feature 4, and so forth. We'll give equal weightage to all the features. But as we know in real life, this might not be true, and that is why again this is a naive assumption. So because of these two naive assumptions, and in the order of importance, this is more important than this. Because of these two naive assumptions, it is called a naive Bayes classifier. Okay, naive is they are too simplistic and not real life practical talks you're talking. But we'll see later that despite these two assumptions, and these two assumptions go a long way in making things simpler for us to actually make a model and give it all the power that it requires of the simplicity that we'll be talking about later. And despite all those things, it is can do a very good work even in a real life scenario and produce very good insights, and we'll talk about those as well. Okay, so let's come back to our discussion here. And we know that probability of x, assuming that naive assumption that we took, and that is why we covered, we digressed a bit and covered that important topic of why it is called a naive Bayes, because of that independence. And we also talk about that if there is an independent event, okay, then we can say probability of those events could be multiplied directly. We do not like subtract anything. Px1 into probability of x2. Here we have only 2, but if we had like 10 different things, you can actually add 10 different features. So x1 here is like systolic pressure, and x2 here is diastolic pressure. Okay, so this solves this. Okay, so for x1, if systolic pressure is low, we'll find what is the probability of having a low systolic pressure. Diastolic pressure is low, then we'll find what is the probability of low diastolic pressure, and that will go into our px2. Okay, and similarly in this particular case, xi given your y, in that also case we have to do xi separately for each of those x1 and x2. So this is your I record number, and we'll split it into x1 and 2. So this will become px given y, I'm calling this as y, okay, is equals to px1 given y, and the same thing we can actually have for conditional distribution also. So if that had been x1 y, then you can just simply multiply if x1 and x2 are independent of each other. Okay, so we'll be using these two notations now. This has come from the set theory that we actually discussed earlier, or probability theory in this particular case. Okay, so if you were to expand this, okay, and now suppose a new data set has come to us, which is x systolic is high and diastolic is low. Okay, now let's try to see the probability of this occurring, and what should the class of this particular data set that is given to us. Now we have to find out the probability of my heart risk being high, okay, given this x, let's call it xt, and then my probability of heart rate is equals to low given xt, okay, and then whichever is higher we'll call that your heart rate is that much. So let's compute this one first. Heart risk is equals to high given xt. We can call it that this is equal to the probability of xt given heart risk is equal to high, okay, into probability of our yc itself, which is heart rate is equals to high, okay, divided by probability of getting such a data that we have got, okay. And now we'll apply set theory to actually break it xt into x1 and x2, which is in this particular case systolic is equals to high and diastolic is equals to low, okay, and we have assumed they are independent, so we are not finding the probability of systolic is equal to high and diastolic equal to low, but alone systolic equal to high and alone diastolic equal to low. This is a very important point, because in real life you might not have such a combination of data existing, but you might have individual levels in the data of those individual features, okay. So let's get to this. So expand this. This is probability of systolic is equals to high given your heart rate is equals to high, because we are computing it for high, okay, multiplied by probability of diastolic is equals to low given heart rate is equals to heart risk is equals to high, okay. So this is the expansion of this part alone, multiplied by overall probability of heart rate is equals to high from our data, irrespective of which class it is, and whole divided by your probability of again having a systolic pressure is equals to high, multiplied by having a diastolic pressure is equals to low, okay. Now let's find out the values for each of these things. Is equals to what is my probability of systolic pressure is equals to high when heart rate is equals to high. So we have heart rate is equals to high only in these two instances, okay. So what is the probability of systolic being high in this? So the probability is 1 for this particular part. So for both of them systolic is high, so probability is 1 when heart rate is equals to high, multiplied by what is this part, what is the probability diastolic is equals to low when heart rate is equals to high. In none of these cases diastolic is low, okay. So this condition is gone, 1 into 0, and now whatever I do divided by multiplied by and so on and so forth, it will be 0, but still we will complete this case for the purpose of illustration so that we get everything. How do we expand this? So this part is 0. Now the third part, what is the probability of heart rate is equals to high in the complete data set? So we have 1 2 3 4 5 6 7 8 instances, out of which 2 heart rate is high. So 2 upon 8 is 1 by 4 is equals to 0.25, okay. And then we will do for the denominator, which is what is the probability, overall probability irrespective of the class of systolic being high, okay. Let's see over here, 1 2 3 4 5 6 7 8 data points, out of which 4 are high. So 1 by 2 is the probability, which is equal to 0.5, okay. And what is the probability that diastolic is equals to low? So in this complete data set, 8 points, there are 2 points for which diastolic is low, which is again 2 by 8 or 1 by 4, 0.25, okay. This is 0, but you now get the idea of how do you compute it. So we will compute it for what is the probability of my heart rate risk is equals to low, heart rate risk is equals to medium, and heart rate risk is equals to high. Okay, and whichever is highest, we'll assign that a class. Okay, you can have like one class out of it, which we will call prediction. Okay, so what we have understood from this, these are the four very high advantages or places where naive Bayes classifier is performs much better than any other conditions. First of all is the noisy data. So what was happening in let's analyze this. So suppose you had this data, okay, and this was your original data set, okay, coming from this particular distribution. Now because of say noise, there will be some data here, some data here, and some random data over here because the noise has shifted this data. In the case of likelihood, what you are trying to do, you are trying to do it somewhere over here and make this sort of a curve. Then we talked about regularization, and you have to set regularization to make it slightly more realistic. In the case of maybe this could be a distribution, okay. And then we did Bayesian linear regression. If you have not seen that video, please see that. We said that we will not set the regularization ourselves, but we will use Bayesian assumptions, and these are very similar assumptions. The only thing was that was linear regression, so it was slightly different. But because of these reasons that we are actually fitting a distribution, and this type of distribution doesn't exist in real life, and the probability of these data points, and that is a definition of noise, the probability of noise is very less as compared to the real data point. Because the probability of these points is very low, they do not affect anything that is based on a generative model that much as it is based on any of the likelihood sort of models. Okay. So if I have a very low probability over here and I have higher probabilities around this, it will do a very good job of actually fitting something like this over here. And that is why Bayesian models, or let's not talk in general, but specifically in case of naive Bayes, it has very good propensity or resistance against noisy data. And in real life condition, as we know, the data is very noisy, and that is why this model still works very well in real life condition. Now the second point, which is a high dimensionality data. So in this particular case, we had x is equals to x1 and x2. Okay, only two features, systolic pressure and diastolic pressure. Let's assume a domain where these are not x1, x2, but x1, x2, x3, and so on and so forth, xn. Okay, so n is equals to 100. If you are trying to actually do any type of Euclidean analysis, which is based on distance or multidimensional aspects of thing based on their distance from each other, then it doesn't work in high dimensional data. This is something called in machine learning as curse of dimensionality. The data becomes sparse in a multi-dimensional space. Okay, just try to visualize it in 3 dimensions, and then you can scale it to hundreds of dimensions. So these are your 3 dimensions. Okay, so this was a plane in say x dimension and y dimension. This is a plane in x dimension and z dimension. This has to be parallel in this regard, and there's a third plane which is in x and y dimension. Suppose this. If now I have one data point over here which has similar x and y, one data point over here which has exactly the same x and y, but z is something different. Okay, now you cannot say that they now belong to the same cluster or even the same class. So now they have a lot of distance between them, because of which fitting any model in this particular case becomes difficult. This is called curse of dimensionality, and you can expand it to 100 dimensions. Now what domains they affect? Obviously they can affect any domain. So if you are into manufacturing or IoT, you can have hundreds of data sensors. Okay, what is the other problem with sensors or any IoT? Noise. So data is too noisy, data has a lot of high dimensionality, you cannot fit many of the models over there. And still I've seen people fitting the data and they do not work out very well. Sometimes you do not even know why they are not working. This might be the reasons. Then come to some other sort of a domain, anything that you have to do with text. Okay, so text, we make features which are based on your tokens, and tokens could be like words or phrases. So suppose if I have a text called I took my dog for a walk. So in most of the text analytics, you will remove all these stop words for I, and then you'll took the remaining words and you'll do the word frequency, or you can do some things on the basis of word frequency, which is TD IDF, inverse frequency, or TF IDF. Okay, or you can take something called a bag of word models, in which you just see whether a particular word is present or not. And we'll talk about more of these things later on. So there is not actually one type of naive Bayes classifier. Naive Bayes classifier is a family of classifier. We are doing a very simple version of it, which is into the discrete category, or discriminant one on the discrete distribution. So we'll be talking about others also later, but let's cover the advantages of naive Bayes first. The third thing that we talked about is less data. So even if we have very less data into our training, then also naive Bayes can work. And where is this coming from? So suppose if I have only these 40 records. So if to train a model I require 400 records, I currently have only 40 records. I want at least a decent model on this, if not a very good model. Maybe if you're going for other methods, they will not even fit, or once they fit, they will actually get so hardened it will give a very bad combination of variance of bias for you, and may not be usable. Whereas in the case of naive Bayes, it will still actually get to a distribution. So suppose if your actual distribution was something like this, based on the 40 data that you gave it, it fitted a distribution which is something like this. This is still usable, and if we get more data, something around here, we can always incrementally, online, real time, keep updating our assumptions of the distributions of the data, and following on, all the things will be based upon the probability distribution as coming from this distribution and not distribution. So we can enhance this model and improve this model incrementally with any new data that is coming. That is also one of the advantages of this model. Okay, and we cover all the 4 point very implicitly, which is that for even a multidimensional space model in which you have hundreds of features, maybe a long text that contains like a lot of words, normally all the other algorithms that will make might be very computationally expensive. This is not only computationally easy, but you can distribute it very well. So if you had seen and noticed earlier, we were computing the probability of each and every class separately. So if you want, you can even distribute that probability, and that probability itself is based on the probability of multiple things that again could be distributed and could in many of the cases be pre-computed as well. So because of all these things, you can make this model very fast, and we can also update this model very fast, because it's only about updating the individual probabilities, and any prediction is actually a combination of those individual probabilities. So any new data that is coming, it will affect one probability or another. You just update it real time. And how do you update the probability? You have the total, so you do not pre-compute exact probability, but you just calculate the totals. What is the total? What is the total on this particular conditions? And then on runtime you can compute the probability. So that way you are just aggregating the count as the data is coming, which makes it very fast, both in terms of making and prediction, even for very large data sets. Okay. The fifth is also a very important point. This is a multi-class classifier. So suppose assume an application in which you have standing topics. You are going for a news ad or any subscriptions in which you have standing topics. Okay, and you need to put every new news or every new article that is coming into one of these. So suppose one of my topics is suppose Intel. Okay, The second topic that I'm interested in, obviously I'm a technology geek, so Samsung. Okay, so Intel comes up with it Cascade Lake X lineup. This should obviously go to Intel topic. So based on the words that is there, whichever model I make, whether a bag of word or frequency of word or TF-IDF, whatever, suppose this puts into Cascade Lake X. Okay. Another second topic comes, say Samsung came up with its Samsung Galaxy S11, or there's been leak into it. I know that this should go into Samsung and I'm interested in Samsung. It should go over here. Okay. But now suppose a topic comes that Intel contacts Samsung for its 5 nanometer EUV technology and how to use that for its upcoming lineup of say GPUs or processor, whatever I think. Now where should this go? This should go to Intel or Samsung. If you have any of the previous or non-naive models that likes that we talked about, which is based on maximum likelihood, they would classify it into Intel or Samsung. And how they would decide? Depending upon what features you have. Suppose if you have the frequency features, okay, then it will count the frequencies of things related to Intel, not just Intel, but things related to Intel. So for example, if there's also this word terminology Cascade Lake X, and that it is found more in topics related to Intel than in topics related to Samsung, those all things will also count. So it can count over that. If you have something like a TF-IDF base, then it will see how many documents you have related to Intel, how many are related to Samsung, and in each of those documents what has been the proportion of inverse proportion of these documents. Okay, and then it will do it for your document. Okay, whereas if you have back of words, you will, instead of counting the frequency, you just see whether those terms are there or not. You get the idea, right? But it will get to any of these two classes only. Whereas from the purpose of my news collection, I would like to see both of them, because suppose if I do not have subscribed to Samsung at all, and by all of these features it was going to Samsung, okay, because that will have a lot of description about the 5 EUV technology, and hence it may actually become very heavy on the Samsung side. So if I do not have no subscription of Samsung, it may not even actually put it to Intel, because it may have a low frequency of it. But if I have like a standing frequency, even if a lower frequency is there, but it is seeing that it could go to Intel, it can still put it into Intel, Samsung, both. Okay. The third problem is, in case of these standing topics, if you have a new subscription app, you can actually add any topic any point in time. Now, if you're playing with any of the previous models, suppose your earlier model has 5 classes and you are doing a classification of all the text that you have, all the news articles you have into these 5 topics. The moment I ask for 6 topics, you cannot actually do justice to it. You have to scrape this whole model and you have to build a new model from start. Whereas in the case of Bayesian model, it is as good as only computing the probability for the 6th class, because each of this probability, as you have seen, we were computing the probability of each of these 5 levels of the classes separately. Okay, now which means that I can even scale such applications for multi-users. Okay, so suppose first user has subscribed to 10 topics, second user has subscribed to say 12 topics, out of which they share say 6 topics, okay, and so on and so forth. You got the idea. So I will have to only train it for 6 plus 4 plus 2, or U1 union U2. We did union, right? So I have to only train it for these, and I do not have to train them for separately. I can just, for each of these topics, I can have a different model. So if anyone asks for a new topic, I just need to add it to my repository. Okay, and if anyone asks for any of the previous model, I just need to like map it that he also requires for this. Which means that irrespective of how my topics are growing, I do not have to scrape and make a new model every time. Okay, so this is also one of the advantages. So now let's talk about types of Naive Bayes classifier. Okay, what we already did one of the simple Naive Bayes. Okay, we covered that, and we also solved some example with that, at least for one of the class levels. Okay, but naive Bayes is a generative model, so it means that it actually senses and makes a distribution. So on the basis of what distribution it's made to sense and what it actually makes, you can have different types. So for example, you can have a Gaussian naive Bayes. I'm calling it NB, but you can always expand it, naive Bayes. So we'll use Gaussian naive Bayes. Okay, so up till now we had systolic and diastolic pressures into their discrete levels, high, medium, low. But now I say, suppose diastolic pressure, let me use a separate color so that we don't get confused. Now let me assume that diastolic pressure is actually a continuous variable, so I'm calculating it or doing it as 100, 110, 115, 120 and so on and so forth. You got the idea, right? Then how would you compute the probability of any new data? Suppose now I get systolic as say high, okay, but my diastolic is equals to 120. Okay, if you do not have 120 in your data, will you put probability as 0? Will not be so, because you only have probability as 125, 126, 123, 130. So it's highly unlikely that you will say the probability of 120 is 0. So what you'll do is you'll actually assume this as a continuous distribution and you'll make and you'll try to fit it into a Gaussian curve. Okay, and then you'll compute the probability distribution function at that particular point from there. So what is this of Gaussian curve? This line is z, which is x minus mu by sigma. But we'll assume for our purpose that this is equal to x so that we can just do a simplistic treatment of this. And in case of a Gaussian curve, how do you define the probability? You have e to the power minus of the z, okay, x minus mu divided by 2 sigma square root, okay, and then you have the same thing almost outside, 2 pi sigma square root. Okay, so this is the probability distribution of a Gaussian function, and on the basis of this, if you have got anything and if you were able to fit a Gaussian curve on the existing training data, then you can compute the probability of any data that is going to come to you. Okay, and then you'll use that in your model. So this is a Gaussian naive Bayes. The third is a multinomial naive Bayes. Okay, what is a multinomial distribution? To understand multinomial distribution, let's understand binomial distribution. Okay, binomial distribution is nothing but a distribution that counts the number of time an event happens. Okay, distribution of counts. And a subclass of this binomial is multinomial in case if this is not one event but suppose multiple types of event. Okay, and you are doing a count of each, and these events are independent in nature, independent of each other, but these are only one of these could occur. So for example, if I have a die, okay, this has 6 sides, 1 2 3 4 5 6, 1 5 3 4 and so on and so forth. If I roll this die, I'll get one of these things. Okay, so suppose this is my probability of getting a 1 on roll, this is a probability of getting a 2 roll, and so on and so forth till getting a 6th on roll. So in any one roll, only one will come. So this way these events are linked, okay, but these are mutually exclusive. If I get a count for 1 in the same roll of die, I cannot get any other count. So if I roll the die 100 times and then I do a probability of getting a 1 versus 2, 3, 4, 5, this will come into something called multinomial distribution. Okay, now just go back and revisit our example on words. Okay, so suppose if I have a sentence, say word 1, word 2, word 3 and so on and so forth, and these events, these are not roll of die, but these are like the occurrence of these words. They also fit into the multinomial distribution because they have a similar thing. I can have like each of these have a frequency. Okay, these frequencies might be independent upon of each other, but they are linked events. Okay, so in a document, that is my assumption. that this frequency actually tells something, and on the basis of which I classify those things. Then let's assume the fourth time, which is a Bernoulli distribution naive Bayes or Bernoulli naive Bayes. Okay, what is this Bernoulli naive Bayes? So suppose if I have an event which has only two modes, either a success or a failure. Okay, and the success has a probability given by P. Failure has a probability given obviously by 1 minus P. If there are only two events, failure would be 1 minus P. Okay, and then I am seeing if I have actually do that something n number of times. Now what is the probability it will get to any of these counts 1, 2, 3, 4? Then that is the probability that is dealt with Bernoulli distribution. Again, if you go back and visit the example of our bag of words based on model, in which we do not count the frequency, but we say whether that word is there in the document or not. Okay, this actually makes this type of a Bernoulli distribution. So for example, you are making a spam filter. Okay, and in spam filter, suppose we have found that it is not about the frequency of individual words that confuse the model, but I'm just finding if whether some of the words like something like lottery, president, Nairobi, or say $10,000 or 1 million, 10 million, okay, or things are in caps. Okay, and this I does have 0, 1, whether it has these words or not, and maybe some combination of this, whether it has the lottery also, prize also, Nairobi also, then it may actually signify something like a spam. I'm not interested how many times the word lottery has come, but just whether it has come or not, how many times that this has come or not. But this will tell me if they have come together or not, because this will be also one, this will be also one, right? So naive Bayes classifier is actually a family of classifiers with all of many variants. So I hope this was an interesting discussion, and if you have not seen a binomial linear regression, please visit that. That's an important topic also. And if you want to visit some of the other classifiers, we'll be actually putting some videos over there. I hope that was useful. Please subscribe to the videos. Thank you.